Okay, so we will now start hyperbolic calculus. We'll start with differentiation, and integration is next. So, differentiating the hyperbolic functions. You have to know that the derivative of sin x is cosh x, the derivative of cosh x is sin x, and the derivative of tan x is sec squared x. This is very similar to trig, because sin x differentiated to cos x differentiated to minus sin x, and tan x differentiated to sec squared x. So we can see again there is a similarity, exactly the same. We had a cos, now we've got a cosh. Here we had a minus sign, here we've got positive sin. Here we had sec squared, here we've got sec squared. So we can see the similarity again. Here we had the minus sign. This has nothing to do with Osborne's rule. Osborne's rule was just purely for the identities. Differentiation is just, I guess, a coincidence or something, but the differentiation calculus, nothing to do with Osborne's rule. Only Osborne's rule if you're using the identities. Well, just like we proved like these identities over here, just using normal algebra and stuff like that, we can also do the same over here. If we want to differentiate sin of x, well, we know sin of x is a half into e to the x minus e to the minus x. So we want to differentiate a half e to the x minus e to the minus x. Well, as a half is a constant, we can bring it out, so we get a half of this. So what we get is a half into, well, differentiate e to the x. Wow, that's just e to the x. Differentiate minus e to the minus x. Well, that's just going to be minus e to the minus x, which is plus minus e to the minus x. So plus e to the minus x. Well, that's just cosh of x. So derivative of sin x is cosh x. The derivative of cosh x, or if we were to differentiate this, then we'd get a half e to the x minus e to the minus x, and that's sin x. So the derivative of sin x is cosh x, the derivative of cosh x is sin x, so the second derivative of sin x is just itself. And the derivative of tan x is sec squared x, using the same sort of principle. I expect you can do that yourself. And that's about it, to be honest, for now. Next we'll do differentiating the inverse functions. So we've got y is equal to a cosh 3x plus b sin 3x, and we have to prove that d squared y by dx squared is 9y. Okay, so we're told what y is, so we can easily find dy by dx. So I should have added that a and b are constants, so we can just leave them out of the differentiation and just add them back later. So a and b are constants. So first let's differentiate a cosh 3x. Well, the a is a constant, so it will just like be taken out, it will just stay there. Now to differentiate cosh 3x, well, the derivative of cosh x is sin x, and just like in normal trig, if you were differentiating cos of 3x by the chain rule, the 3 would come out because we multiply by the derivative of the inner function, so it would be minus 3 sin 3x. So in the same way here, we just use the chain rule, so the derivative of cosh 3x will be 3 sin 3x. So we'll get a multiplied by 3 sin 3x, so 3a sin 3x. And then for the second term, we get 3b cosh 3x when we differentiate it. So we found what dy by dx is, now we need to find d squared y by dx squared. So the second derivative is equal to 3a, because that's just a constant. Now differentiate sin 3x, well, we did that for this one over here, so that's going to be 3 cosh 3x. So we're going to get multiplied by 3 cosh 3x. Well, 3 times 3 is 9, so we're just going to get 9 cosh 3x. And then we're going to add that to the derivative of 3b cosh 3x. Well, cosh 3x we differentiated here to get 3 sin 3x, so 3 times 3 again is 9, so we're going to get 9b sin 3x, and this should be 9a. Okay, well, we found the second derivative, but we had to show it's 9y. Well, y is a cosh 3x plus b sine 3x, and we can see we've got that here. We've got the a cosh 3x here and the b sine 3x here, and then we've got 9's on either side, so we can just factor the 9 out. So we get 9 a cosh 3x plus b sine 3x, so that's 9y. So we've got that question. So we've proved that the second derivative is 9y. Now let's try this exam question. So it's a 7 marker, so oh my gosh, it's going to be a lot of working. It really isn't. So the curve C has equation y is equal to 31 sine x minus 2 sine 2x. So right, so straight away we can see that we've got this sine 2x, and here we've just got sine x. So we're going to have to convert the sine 2x in terms of just sine x or something like that, because we have to get everything in terms of just like 1x. So determine in terms of natural logarithms. So natural logarithms, we know we're going to be using r sine at some point. The exact coordinates of the stationary points of C. Right, stationary points, dy by dx is equal to 0. So dy by dx equals 0 at stationary points. Well, let's just work out what dy by dx is. So dy by dx, so 31 sine x, that's just going to differentiate to 31 cosh x, minus 2 sine 2x. Well, just like in the question we just did, that'll be 2 multiplied by the derivative of sine 2x, which is 2 cosh 2x. So 2 times 2 is 4, so we get 4 cosh 2x. So now we just have to set this equal to 0. So we can't solve this unless we have everything in terms of like just 1x. So this is 31 cosh x minus, right, now cosh 2x. What identity do we know for cosh 2x to make it into a normal x? Well, right, well, cosh of 2x we know is sine squared x added to cosh squared x from the video on Osborne's rule. But then if we make this substitution, we'll have cosh x here, sine squared x here, and cosh squared x here. So that's not really helping. So we have to try and transform this. So first let's just deal in terms of normal tricks. So if we have cos 2x, we know that that is identical to cos squared x minus sine squared x. Well, we should know from A-level maths that this identity of cos 2x has many forms. So one of the forms that will be helpful here is to change the sine squared x into 1 minus cos squared x. And what we end up getting is cos squared x minus 1 plus cos squared x, so we get 2 cos squared x minus 1. So now over here, if we use Osborne's rule, we're just going to get 2 cosh squared x minus 1. So what we can say is that cosh of 2x is equal to 2 cosh squared x minus 1. So what we can say is that we're multiplying 4, and then the cosh 2x is 2 cosh squared x minus 1. That's equal to 0. So I'll just put that on the right somewhere. Alright, so now let's just expand this. So what we get is 31 cosh x minus 8 cosh squared x plus 4 equals 0. Now this is going to be hidden quadratic because we've got minus 8 here. We'll just move everything to the other side. So what we get is 8 cosh squared x minus 31 cosh x minus 4 equals 0. Now we can just use the quadratic solver on our calculator, and we get 4 or negative an eighth. So instead of just writing cosh x equals 4, cosh x equals negative an eighth, we'll just pretend we've like done the work and factorized it. So if we get values of 4 and negative an eighth, the brackets are going to be, for negative an eighth we'll get 8 cosh x plus 1, and then cosh x minus 4 equals 0. So we just like factorized it. So now we can say that cosh x is equal to negative an eighth, or cosh x is equal to 4. Alright, well, we should know that cosh x can never be negative an eighth, because the cosh graph, if you remember, was like the deep quadratic. Well, everything's just above the x-axis, so it can never be negative, so it can never be negative an eighth. So cosh x can never be negative an eighth for any real values of x, for all real values of x. So therefore cosh x equals 4. Well, cosh x is equal to 4, so x is equal to arc cosh of 4. Well, we know that that's ln of 4 plus the square root of 4 squared minus 1, which is 16 minus 1, which is 15. So ln of 4 plus root 15. But the question says, determine the exact x coordinates of the stationary points. So there must be more than one. Well, for there to be more than one, well, this is just one x coordinate. We don't have to find the y coordinate or anything because we haven't been asked to, but that's just one x coordinate. Well, if you remember from when we did the first video on the graphs, the arc cosh x graph was like this, because we said that, oh, this becomes like a one-to-many function then. But this is the actual graph of cosh x, of arc cosh x, but it's just that we couldn't have the one-to-many thing. But this is still the full graph of it, so we're still going to have the plus minus, so that should still be plus minus. So what we can say is just make that a plus minus, and this is pretty much should be our final answer. So that should be 7 marks right there. So you see, that's like taken not even like half the page, and we've got 7 marks hopefully. Let's just check. So we've got oops, that's too big. Okay. ln of 4 plus minus root 15, ln of 4 plus minus root 15. So that is 7 marks for us right there. Okay, now we are on to differentiating the inverse hyperbolic functions.